access.
Hello, I'm Mike. I'm introducing Ali, who's a researcher visiting here from Belgium, working in Dirk's lab. And without further ado, here we go.
Thanks. So, hello everybody, thanks for tuning in. So today I'm going to give you a presentation about the work that I've been doing during my PhD. I'm still doing it. So it will be about neuromorphic sensor fusion algorithms for with applications to drone navigation tasks. So we'll play really with spiking neural networks and with learning techniques such as SCDP, so spike time independent plasticity, unlike really backpropagation kind of techniques. So we want to focus really our work on more bio-inspired kind of learning. So I'm Ali, I'm a PhD researcher at imec and the Leuven in Belgium. And I'm a visiting researcher here at the lab of co-authors at UCSD. So here's the outline of the talk of today. So first I will go through the kind of baseline spiking neural network architecture that we are using. So really I will describe this SNN STDP framework. So this framework allows you to learn in ensemble of spiking neurons with STDP plasticity. And I will motivate it and explain you why we adopted the approach we adopted there. Then after that, we'll move towards the first application of this network to for people detection on drones. So we have drone equipped with an event-based camera, so a retinamorphic kind of camera that will need to detect people as it is flying. And then finally, we'll use this SNN STDP framework for performing SLAM, so simultaneous localization and mapping, meaning that the drone will need to basically online try to learn how the environment looks like, that is the map of the environment, and at the same time will try to locate itself in that. And this will be done with a fusion of event-based cameras and radar. So before let's get to know a bit imec and the Leuven. So here you can see a map of Belgium. And you see that our headquarters is located here. So imec is this big R&D center in Belgium that does research really spanning the whole gamut of electrical engineering. So from device physics to chip manufacturing to computer science and robotics as well. And it really started as a spin-off of the Leuven, the University of Leuven. And here you can see a picture on the Ironware campus of electrical engineering. Near the imec forward. And our company imec is presently worldwide, so we have also facilities in Orlando, in Florida, we have facilities in Berkeley, also in Asia, and the Netherlands. And yeah, so this is really this hub for R&D research. So now, without further ado, let's dive into the first chapter of this presentation, which is about performing learning and spiking ensemble of spiking neural networks via STDP, spike time independent plasticity. So in the recent years, we've all seen really the amazing effectiveness of backpropagation to time and strongly gradient descent techniques for training spiking neural networks. In fact, I believe that these techniques were first originated here in CMD. And so it's really those techniques have been very useful and have led to a lot of successful at-mind trainings. But even though very useful, these methods have some caveats. So from a biological point of view, they are not really bioplausible since they are doing backpropagation. They are not local learning routes, they're not akin to heavy elasticity. Also, another thing is that they are not really necessarily hardware friendly. So if you want to do learning at the edge with very little power, well, we know that this is a problem when you're using backpropagation type of algorithms of such as weight transfer. And this idea that you need to access weights in transformed manner when you do backpropagation function. On the other hand, we know that spike time independent plasticity can be used to perform learning at the edge in very low power SNN chips. And so the question then arises, how can we build an effective framework that can train spiking neural networks with SCDP? So a kind of very bio-inspired kind of framework. And the challenge really here is that, well, we know that there exists some prior work, of course, a lot of prior works on training SNNs with spectrum networks and their plasticity. But what we observe of them is that they don't reach performances as high as the backdrop control. And so they might work well in toy cases and toy data such as elements, for example, but they have a hard time scaling sometimes to real world problems. And so this is the challenge that we're trying to address. To further motivate really why redistributed gradients in backpropagation works so well, here we have just a small example of a spiking law network doing radar gesture recognition. So we do gestures in front of the radar, and we feed this input data in a spiking format to the network. And what I just wanted to show you here is that indeed, training a network backdrop reaches thinner accuracy than the value counterpart, the CNN, which will be normal backdrop control. But what we want to do is get rid of these backdrop trained SNNs and train them with spike time intelligence. So let's now decide on the approach that we wanted to adopt to build this kind of SCDP-driven system. So we adopted an optimization-based approach to SNN series. So what do I mean by that? First, we need to understand what most, let's say, SNN SCDP systems, such as liquid state machines, how they are designed. Well, what we see is that they are designed in a very kind of heuristical way, very intuitive way, in the sense that a typical way of designing a liquid state machine would be the following: you would initialize an ensemble of excitatory neurons, and then connect them to another pool of inhibitory neurons. And these inhibitory neurons are connected back to the excitatory neurons in a way such as that we create lateral competition between the excitatory neurons. And then you have a set of input weights to these excitatory neurons, and you apply STDP to these input weights. And what you hope is that through the lateral competition between the excitatory neurons, STDP will learn a useful set of features, a diverse set of features in the input. Well, the connectivity also is random. So the topology of the network is initialized in a random manner, but still so as to perform to provide lateral. As you can see, it is quite, let's say, heuristically defined and defined in a bottom-up manner with inspiration from biology. And so the approach that we wanted to adopt is really the inverse, in the sense that we wanted to say, okay, we want to build a certain SNN system. Instead of starting from the bottom-up approach, let's start by saying the following. Well, we want our system to infer a certain output C, so C is the vector of output spectrum, to learn a certain set of weights phi, such that it minimizes a certain energy function, while it receives the input spike trains as is the vector input spike. So this is a very generic kind of formulation, of course. But what we are saying is that we want our SNN SCDP system to derive itself from the minimization of a certain optimization point. And you see that this is a top-down rather than the bottom-up. And so, as you will see in the next slides, we will have two questions that we need to answer here. First, how to choose the energy function, how to choose a sound energy function for this problem. And secondly, how the minimization of the energy function relates to the specific topology or the specific architecture of the underlying SNN SCDP substrate that solves this minimization problem. So, so first let's choose a sound energy function for our problem. Well, here we come back to the biological inspiration. So from the bottom up, we know that an ensemble of spiking neurons equipped with SCDP plasticity does really two things. First, it infers a certain output while providing competition between these output elements. And at the same time, it jointly learns a set of weights. Well, there's a striking resemblance between these two steps and the problem of joint dictionary learning in sparse coding, the basis for students in classical machine learning. So, what is this problem? The dictionary problem is shown here in this equation. So, given an input S, the different learning and sparse coding problem tries to infer a sparse code C and learn a dictionary or a set of weights, such that it minimizes the reprojection error between the input S and the source C through the dictionary. It also observes some regularization constraints on the sparsity of the output C through, for example, Neuromorphic regulation. We can also add some weight decay for values normalization for the weights metrics. And so here, this energy function is in fact a standard energy function for a problem, because the lasso term here will provide a competition in each element of this output C system, because, well, the lasso is trying to push each component to be exactly equal to 0, and components are competing against each other to be non-zero. That's where the sorting comes in. And, well, so at the same time that it's doing this inference, it is also learning the weights 5 through this minimization, which is akin to a notary problem. And so the question then becomes, can we design an SNN topology in architecture where the dynamic outflows, meaning the outputs and the weights, dynamics of the output and the weight, converge to a solution of this problem? And there are many motivations for adopting this problem. For example, in the maximum body of the insect strain, we know that there are things happening there that are akin to sparse coding. There's a lot of literature about predictive coding, a group of also in Berkeley. Also, a lot of works linked to that are the spiking restricted Wilson machines that were generated in the lab here in Sydney. So now let's see how we can solve this energy function using a spiking network with CP. Before diving into the mathematics, I want to give you already the network architecture that, in fact, you can show that probably solves this optimization problem, although, of course, with some approximations as we need to do during the derivation, what we will cover later. So I'll just go through the architecture first, and then we'll go through the mathematical details. The architecture is composed of two ensembles of spiking neurons. You have the coding neurons, which is a layer of spiking neurons, and you have also the error neurons, which is the second layer of spiking. The input spikes are represented by this vector S, and T is the time, are fed to both the coding neurons and the error neurons. Through a certain input weights, P, what we call P, and all the weights here are independent of each other. You also have a recurrent connection through the lateral weight W, taking the output of the coding neuron and feeding them back to the layer, because this architecture will, as you can see, is a recurrent one. And also the last thing is that you have a feedback weight connection through the weight matrix out F from the coding neurons output to these error neurons. And then the output of the error neurons are fed back as well through the input weights to the coding neurons. So basically, we have a recurrent architecture here in the green part, and then a special add-on part through these error neurons here. And we will apply STDP to all the weights of this network, and all the weights are independently evolving. And what we can show, and you see the all details I invite you to this manuscript, we can show that when you apply STDP to the methods described there, the weights of this network will converge to, let's say, for example, weights that are related to the dictionary of the dictionary problems. For example, feedback weights will converge to the dictionary matrix. The input weights will converge to the transpose of the dictionary matrix, and the lateral weight will converge to also something related to it. And it will kind of open up the black box in the next slide. So first, we're going to go on how to really influence, so how to output the C, the output of spikes of the coding layer. So this kind of optimization problem we're shown here, when you're optimizing for both the output C and the weights 5, are typically solved in a typical manner. For example, you would consider 5 peaks and infer the next C, consider C peaks, infer the next 5. And this is also what our network is doing in this. So first we need to understand how to infer C considering 5 peaks. Well, when you pose this problem here, so the minimization only over C, the problem becomes really a lasso problem, since we have this L1 minimization and this doesn't play a role. Well, we know that to solve a lasso problem, it is typically done using proximal gradient descent. So, how does that work? Well, in proximal gradient descent, what you will do is that you will consider only the, let's say, mean loss function here, this mean loss term, it's a correction error, and you will perform a stochastic gradient descent step for this, let's say, the correction error. So the gradient of that term with regard to phi is given here by transpose times this error, this phi c minus s term. And we'll just take the gradient step with the convergence rate of L1 given the previous C. But then to take into account the L1 constraint that we have in the problem, we will use a proximal operator, which is an operator that will project the result of the spike, the stochastic gradient descent step that we take here into the space of constraint that is synthesized by the L1 constraint. So we pass the result of the stochastic gradient descent step into this proximal operator to get the next. Well, what you will see is that the coding neurons in our architecture are in fact doing this in a recurrent manner. So you can see already the recurrence here, where C can be seen as a hidden state of the network. And well, you see the recurrence here, where we have a new state C that is fed then that will become the currency, etc., etc. And what you will see in the next part of the slides is that we'll do this using a layer of spiking. We do that as follows. We just rewrite this argument as the following here. I just rearrange the term here. Well, we see the apparition of two wave matrices. The lateral wave matrix W that processes the C vector, and the input winds. We pass this combination of spikes to an exponential decay filter to estimate the instantaneous rates of that combination. This instantaneous rate is considered as an input current, and this input current will then be fed to a layer of spiking neurons. And the important thing here is that this layer of spiking neurons must be such that they behave in the instantaneous rate domain as the proximal operator in order to perform this proximal descent. So the proximal operator to the L1 node is shown here in orange. It's these two values back to back, this kind of nonlinearity. And what you can see is that you can kind of simulate or approach or approximate this proximal behavior using two leaking integrated fire neurons put in a push-pull manner. So we use two leaking integrated fire neurons receiving just, so for example, one is receiving the current J, the other one is receiving minus J. And the output of that other one is considered of negative polarity. And so using this pair of push-pull leaking integrated fire neurons, we are indeed having a nonlinearity that kind of approximates the proximal operator when you are out of the saturation zone. And so that is it really. We can then pass this input current to a layer of push-pull spiking neurons in order to achieve the proximal descent effect during the SNM. An interesting thing to remark here is that the strength of the lasso organization, classical sports trading, is directly linked to the threshold of movement. So as you make lambda 1 bigger, the dead zone of the proximal operator with yellow will grow, but this is same as if you would increase the threshold of the movement, the dead zone, the place where the nodes are silent, will grow as well. You see here a elegant link between this lasso parameter and the threshold. So now that we know how to infer C, we want to know how to learn the weights phi using STDP. And before delving into that, we need to understand really what STDP does for us in that instantaneous spike rate domain in which we are working. So spike time independent plasticity is really shown here in this graph. So it consists of a rule that is really akin to the Hebbian rule. So neurons that are together wired together, but it does it in a spike timing domain. So if you have a certain neuron that spikes after receiving certain input spikes, then this weight is increased. If it spikes before receiving a certain input spike, then it means that they are not related together, so the weight decreases. And this increase and decrease are here given by the standard double exponential STDP curve, STDP rule, where tau is the difference between the post and pre-synaptic. So then what we can write down is what would be the weight modification at time step t, given a certain train of postsynaptic spikes and a certain train of presynaptic spikes. We can write it as follows. So each time the postsynaptic spike at time step t is equal to 1, then it is a matter of convolving all the presynaptic spikes with the STDP curve. So this would be simply the equation giving you the weight change of the synapse given the postsynaptic spike train and the presynaptic spike train. But under this formulation, this equation is not really that useful because we don't really know what those spike trains are. We record them, of course, but it's annoying because, well, we need to store a lot of memory. Perhaps those spike trains are very long. So a good thing that we can do is to consider them stochastic. We can consider that both the postsynaptic spikes and the presynaptic spikes are stochastic processes. And therefore, we consider the expected value of the change in weight. And so when we take the expected value of the change in weight at time step t, we can then apply the expected value to the only stochastic elements here, which are the post and presynaptic spike. And then we can just use a simple formula for the expected value of the product of two random variables to derive this as the following here, where you see the first term, which is given by the product of the mean value of these two stochastic variables, and another term that is dependent on the covariance between these two variables, postsynaptic spikes and presynaptic. Well, in a real spiking neural network, since each neuron receives input from many other neurons, so you don't have only one source, you have many sources that causes the output neuronal spikes, the postsynaptic activity, in fact, can be considered independent of each individual presynaptic activity because simply of central limit theorem can be. And so for that reason, we can safely ignore this covariance term. And so now we have a simplification of STDP. We know that in the instantaneous spike wave domain, we can safely approximate the effect of STDP as the product of the post-synaptic spike waves and the presynaptic spike wave. And also we have this additional constant here, which is related to the STDP parameter. Now that we have established this step, we can now understand how to learn the dictionary type. So in our dictionary learning problem, we need to minimize this term here. So this recursion error here. And this can be simply done again with stochastic gradient descent. So this would be the stochastic gradient descent step that you will do to verify. Here we see a product between these output spike trains of the coding neurons, C, and another term here, which is a form of error term by C minus S. And so then what we see here, when we look at this equation, is that we need a second population of neurons that will then code the error that the ensemble is doing as spiking activity as well. And so this is the role of the error neurons in the network that I showed you. These error neurons, what they do is that they, as you will see in the next slide, they will receive the input S and the output of the coding neurons through the feedback weights that is akin to phi, and will then produce an error spiking activity, which is, let's say, related by C minus S. And so that now we see how we can learn phi. Now that we have the error spikes that are coming out of the error neurons, we can apply STDP between the error spike trains and the output spike trains in order to perform the product between these phi C minus S and C. And by doing that, we can then learn phi through STDP. For all the other ways of the network, learning follows a similar kind of approach, which is very exactly the same, it's very similar, but although the weights are transposed of each other, but it's just a detail. You can see those details there, but really the methodology that is used is exactly the same, but just adapted to the format of each weight. Okay, so here again we have the network architecture, and you see again that these error neurons receive the input S and the output C through the feedback weights F, and therefore their output is akin to the error activity. And as you see here, we feed it back to the polyneuron, and a CP is applied. For example, applying a CP for the error neurons between the output error and the C of the polyneuron will again give you the product between E and C that we transpose manually, and this is why basically F will give you the learn fly and polyneuron will learn fractions. That's yeah, some symmetry in the weights. So now that we have this network, we want to try it on classical neuromorphic benchmarks. And we used two data sets. So the first one is the neuromorphic MNIST dataset, which is in fact like the MNIST dataset, but just recaptured using an event-driven camera. So they would show MNIST images on user screen and had and then this camera that is in seconds in front of this image and recording the spectrum. And we have also another data set that we use, which is this gesture recognition data set, which is called the IBM DS-128 gesture recognition data set, the Leuven class data set. And so we used both these two neuromorphic data sets to conduct our benchmark. What we do is the following: we just feed data from these data sets to our network architecture here in a fully connected manner. And after some iterations on epochs, the weights of the network will learn meaningful patterns. So here you can see the patterns learned, the visual fields learned in weights of the network. For example, on the Neuromorphic MNIST, you see that what is learned in the weight is akin to, let's say, abstract digits or combination of digits. For the gesture recognition, the patterns are a bit more abstract here as well, but you see some patterns. And the interesting thing is that so after training that in a non-supervised manner with a CDP, we then just learn a linear SVM classifier on the outputs of the SNN. So we refeed the data set into our SNN after learning. So that's where the SNN fixed. And then we refeed the whole data set, the training set into it with the fixed weights. We re-encode a data set in spike format. We aggregate some statistics of the output spike trains, such as the mean weight basically, and we then train a linear SVM on this encoded data. And you can see here the results, which show that in fact this method compares quite favorably with other methods. So for example, on the gesture recognition piece, compared to recently proposed SCDP-based solutions, you see that our method compares pretty favorably. On the MNIST of neuromorphic MNIST, we also compare against other, let's say, same class kind of techniques with one layer, a few layer kind of techniques, and we need to see competitive. Okay, so now that we have established this, let's say, SNN SCDP framework, we wanted to use it to really solve perhaps, let's say, more large-scale problems, such as drone tasks. And now I will really cover first task, which is people detection, using our SNN SCDP framework, but shown but using a convolutional setting. So it is not all the same, but the dictionary learning is just a convolutional dictionary learning. So before diving into the full action, I just wanted to show you the data recording setup and we'll also use for all the other experiments shown here. So we have this drone back in Belgium, and this drone is equipped with an event-based camera, Davis 346, event-based camera that provides also RGB frame as well for convenience. It also has a radar, 79 gigahertz frequency modulated continuous wave radar. And this platform is really the platform that we have been using for experimenting with central fusion, with neuromorphic central fusion between a radar and cameras. So a little recap, I'm sure most of you know it, but so the way an event-based camera works is different than the way frames in normal RGB camera works. So, for example, if you have a certain rotating disk with these black dots, a normal camera will just take snapshots of the scene of that rotating disk. Whereas the event camera will only show you, let's say, the changes in intensity. So you will only see that black dots returning, and so it will produce you this spatial-temporal, let's say, vortex of events, of spikes that are not only spatial, because well, we have some spatial movement, also there's this time component. And so the DVS camera is composed of pixels, meaning that fire spikes whenever the change in light intensity comes with a certain threshold. You do that in an asynchronous manner as opposed to logic. Here you can see also an example of radar detections. So a radar will, for example, typically provide you detection information. So, for example, if I have certain objects, reflector object somewhere in the scene, it will provide you this bird's eye view, this range azimuth kind of view that you see here. So this radar detection was acquired while it's flying here between these shells, this kind of storage eyes. You see the detections follow the storage. And so now that we have this broad platform and we can report data, we really want to do some interesting stuff with that, but using our SNN-CDP kind of framework. And so what I will show you next in the next slide is two things. So learning to detect people. So basically from event data, learning to output attention maps, as you see here. And the second thing I will show you is to perform simultaneous localization and mapping, which is that the drone will basically navigate in that indoor environment, this kind of warehouse environment, circles like that, and the SNN-CDP based algorithm will then need to reconstruct the map of that environment as well as locating the drone in that environment. So first, let's address the people reduction approach that we adopted with SNN-CDP. So this is the blueprint of our system, really. We have event data coming into this SNN-CDP system, followed by a neural activity readout. So it is a bit the same as the linear CVM that I showed you for the classification. So we need this activity readout plane. Here it will be different. So we have sigmoidal neurons. And then the whole architecture is convolutional, and therefore it takes an image in and produces you a map out, since the whole architecture is convolutional, and this map is in fact an attention. We learn to do this kind of attention. Yeah, so this is the network architecture that we use. It is composed of two layers. So the first layer is the SNN-CDP layer, but in a convolutional setting. So you can see it as a bit the same as the fully connected SNN and ensemble I showed you before, but just that you would sweep its visual, let's say, zones, visual inputs across an image with certain pop size and stride size. But apart from that, everything is similar. So we have this first layer of convolutional SNN-CDP. We sweep this visual across the inputs. The spike activity of that layer is then normalized. So in fact, we use, for example, 64 neurons, 64 filters in the filter bank, convolutional filter bank. And so for each visual field, for each hub, we then obtain 64-dimensional vector, and we normalize these 64-dimensional vectors by dividing by the sum of the absolute value of the rates, spiking rates, over a certain time frame. It's just a normalization. You can see the details in the manuscript. It's just there to provide invariance to the event density at the input. So some part of the rooms may produce less events, some part of the rooms produce a lot of events, and so by doing that, we help with the system being invariant to the density of events. Then it is followed by a standard scaling procedure, which is similar to rational. Yes, so we remove the mean divided by the standard deviation. And this is also, let's say, that the mean and the standard deviation are simply aggregated online or learned from the data, from the statistics of the output of the normalization step. And finally, the output of the center of scaling is fed to a convolutional layer here, followed by sigmoidal units. And so bear in mind that here at this stage, we have spike rate, we have spike rate, so we converted spike rates here. And so the output here must then behave like a tension map. That's what we want. The way we train this model is that we will have this drone moving around in an open space for now, with different people walking in front of it. We also get the RGB data out of the camera, and we can run a YOLO associated vector to provide us with a bounding box. And online, as the data stream is being fed in its natural order, we simply try to make the readout stick to what the YOLO is giving us as a zone. The bounding box of the YOLO is then the zone where the attention map should be equal to 1, the maximum value. The last thing is that to successfully, let's say, be able to perform this kind of detection, we needed to incorporate a third factor, let's say, learning system from the readout side to the SNSCDP side. So there is some, let's say, third factor supervision coming from the readout to the SNSCDP through the additions of this deeper signal spectrum that we'll detail in the next slide. That we are trying to steer the SCDP dynamics in a way that is let's say, more informed by the supervised loss that we have at the readout. So as our loss function at the readout, we use the focal loss, which is a bit the same as the percent of the really, but with the addition of this additional gamma exponent here. And the focal loss is really interesting in cases where you have imbalance in your JSA. So, for example, in our case, we have most, let's say, situations that the drone will encounter, a human is not present. This is just by nature of how we acquire the data. And for that reason, we will tune gamma a little smaller than 1, so compared to what normal percentage would be, in order to rebalance a bit the loss in favor of the fact that we have less examples when a human is present. So yeah, this is a classical loss used for this. In order to create these third factor spike trains that feed back into the SNSCDP side, we needed to do some approximations. First, we approximated the output of the SNN in a very crude manner by saying that the output spikes are really, let's say, akin to this term here, meaning the flight transpose, so the input rate SNN, times the input S, and with a certain normalization constant here. What you can show is that this approximation holds really at the very beginning of learning, when the weights are still random. The flight transpose phi kind of terms are diagonal still, and so it would reduce this kind of constant.
Why do you need to approximate the output?
Oh, because simply if we don't do it, we cannot simply feed a third factor kind of modulatory signals and use SCDP to take that into account as well. It becomes way more convoluted. Since in fact, the activity is through this kind of proximal operator kind of nonlinearity, we don't want to take explicitly into account the nonlinearity of the neurons, like in the brain descendant kind of thing. And so we use this linear approximation to this nonlinear network that we have in order to just help it a bit. And really, it helps it quite a lot in fact. We don't use it, results are not as good, but I agree that indeed it's a very crude approximation. It makes things easier and makes things more local. So the signals can be, let's say, used together and undergoing SCDP plasticity, all in a local manner, without resorting to using surrogate gradients of the nonlinearity.
You say stochastic gradients, that is being able to set.
The surrogate gradients.
Surrogate gradients.
Yeah, so for example, we would say, well, if you really want to do it properly, what you would do is that you have to take into account the derivative outputs of the spiking neurons with regard to their inputs. And since it is nonlinear, you need to have a certain derivative that is like a Gaussian bound function, like the surrogate gradient instead. But we don't want to do that. We want to things again with SCDP. So we just want to have a spiking spike tree that is this teacher spike tree. We want to have the spike tree that are already present in the SNN and combine them only with the SCDP. Don't want to use any let's say other function that we pass it through. That's why we do this simplification. Yeah, so under the simplification, you can write the derivative of that loss, the real loss with regard to the SNS in the weights as the following. When you see here the input to the SNS, and here this term here, as you see, is really the derivative of the loss with regard to the inputs of the readout. So C is the output of the SNN, which becomes the input of the readout. And so this term here can be fully computed at the readout side, and then fed back under spiking format to the SNN side, and combined again using SCDP. You see the product between S and this term here. And we remember that SCDP acts a bit like the product of the mean values. And again, we do that same trick here. And so V here, this term can be computed at the readout side and transform into a spike tree by simply feeding it to a pair of two leaky negative further nodes. So this becomes a true factor supervision. Yeah, so we did some experiments with threefold cross-validation. So what we did is that we learned the system on, for example, one acquisition with one subject, and then after, for example, 2 minutes of the data stream, we stopped showing the data stream, and we stopped the learning. We freeze the weights, and then we basically have another acquisition, test acquisition that we pass through, and we want to assess the performance, and we did it 3 times in threefold cross-validation manner. And so we assessed multiple things using the cross-validation. First, the impact of gamma. So gamma was this parameter setting the total loss balance. But you can see that indeed gamma is very interesting to tune. So there is a form of optimum where gamma is 0.5. So these are precision recall curves. The precision recall curves give you an idea. It's really the standard way of assessing object detection problems. And basically, what you would like to do is to have a precision recall curve that is as close as possible to the 1-1 point that is here. So having a precision of 1 and recall, no false alarm, and detecting all the time what should be. What you see here is that the best kind of precision recall curve was obtained with a gamma of 0.5 here. So now it already shows that tuning this gamma parameter has a sensible effect in this. So then we tune, yes, we tune gamma to 0.5 and then we left it that. Then the second tuning step that we did is, well, we have this trifector supervision signal that I just discussed in the slide before, but we still have the unsupervised contribution of the CDP is still there. And so it's interesting to understand if having a bit of this unsupervised contribution, does it help or not? And in reality, it helps as well. So it helps, in fact, leading to an increase in precision of higher recalls. What you see is that if the lambda U and lambda S are on the hyperparameters balancing how much the third factor supervision signal is strong compared to the unsupervised one. And what you see that again here there is a form of, let's say, a single parameter to use, which is in image. And then the final test that we did is to compare the detection performance against a same size CNN, so classical CNN using Leuven relations, and we chose the squeeze network calculator, which is known to in fact achieve Alex step level accuracy in imagement, while using very little amount of weight. So it has a size of 500 kilobytes, which is more or less the same as our network, so it was fair comparison. And what you see here is that this CNN processing these let's say DBS images, we aggregated basically doing 5 millisecond kind of time window aggregation, performs less well than our CDP system. And we think that this is due to the fact that our CNN system is a recurrent system. It's fine dynamics as well. Of course, an interesting thing would be to as recurrence to the CNN to further comparison. But this already shows that this kind of system evolves further compared to just an off-the-shelf system. That was the motivation. Here is some videos of the system in action. So those are test sequences. What you see is that the system does an okay job or a very good job at keeping this attention kind of attention lapse, building up good attention lapse. But as you see also, it suffers from some false alarms. In fact, sometimes it can suffer from a lot of false alarms due to the very convoluted background. For example, here is pretty clear in that corner. Yes, and so this is what causes its necessary call to properties. But yeah, at the time that we came up with this work, this was one of the let's say complex application of the CDP, even though indeed it deserves additional work to address these false alarm still. Okay, so now let's go to the last chapter of the presentation, which will be about simultaneous localization and mapping. So here the idea is that we have this drone that will be flying in this indoor storage environment, and it will need to construct a map of the environment as it flies around. So the online should be able to construct a map. And at the same time, it should localize itself into that map. And there's also an additional thing here. So we'll use a slightly neural network of the CDP, again using our same framework. But the learning of the SNS CDP system will also be online in a continual learning manner, meaning that at the beginning, the SNN is initialized totally randomly when the drone first starts to move, and the drone is expected to perform SLAM while tuning, learning this SLM in a continual manner as it goes around the world. So there's also this aspect to it. The SLM is not retrained and then used for SLAM. No, the SLM is initialized randomly and learns at the same time that the drone is flying and doing the SLAM task. Okay. And so when you want to do this kind of continual learning, you run into quite some problems, because it is well known, for example, that if you want to train a simple neural network on ends without shuffling the units, for example, train only the ones and the twos and the threes, it doesn't work that well too. This is because when you use learning methods that are different type, stochastic different type methods, what they're assuming is that the stochastic gradient that you have, that you're using to modify the weight times the t, well, it's a stochastic, you see that the stochastic gradient, but in expected value, this stochastic gradient should converge to the gradient of the full loss, as if you had the whole data set available. And so the way to achieve that typically is to shuffle the data set. By shuffling the data sets, you make the trial distribution from which those gradients are really generated stationary during learning, never moves, and therefore the expected value converges then to the gradient of the full loss. But then in our case, when we have this drone flying around, this is not the case anymore. We are not under this shuffle data assumption. Rather, we have a non-stationary stream of data, meaning that sequence data inputs, let's say, look the same. So we have a big problem of data imbalance. And so we'll use this again, this dictionary learning based kind of framework that I just put back here, the equation here. And so given the input S, which is, for example, the spike trains coming from an event camera or RGB frames, for example, again, you want to learn online in continual manner, the weights 5, and online you want to produce the output C, and then feed these descriptors, this latent code C, to a SLAM backend. The backend will take these descriptors and will then basically assign them to each pose of the drone, and then detect loop closures by just template matching these descriptors with future descriptors that it sees. So if in the filters, it's the SLAM backend sees the same kind of descriptor C as it saw before, it understands that it's in the same place. So we perform a loop order and correct the map accordingly. So that's how we plan to use this determined learning kind of idea. Well, but still we have this problem of imbalance, this problem of non-stationarity of the data stream. And here we did an observation. So we observed that the original SVM formulation, supervector machine formulation, original vacuum formulation, is in fact quite robust to data imbalance in the data set. And this comes from the fact that, well, the hyperplane that an SVM could learn, you can write, of course, as the combination of all the data in the data set, all the inputs S, multiplied by their Lagrange multiplier alpha I. And, well, the SVM has this property that a lot of these alpha i's can be exactly equal to 0. So it has the sparsity of the Lagrange multiplier property. And this is very interesting because it means that the SVM has the ability to understand what data points S are redundant and that we don't really need to incorporate in the learning of our hyperplane. Because if we were to incorporate it, perhaps we would overfit on that dominant class. And so, for that reason, what we will do is that we'll kind of use a similar approach. We want to provide this SVM, this sparsity kind of property to our dictionary learning problem. So then here the main result that we have derived, and you can check the relation here in the manuscript, is that you can achieve a similar effect as what is done in the original SVM. So for the learning of the Phi dictionary, which is the hyperplane methods, using a certain stepwise metric. So we have this stepwise metric, which is in fact approximately equal to the difference between successive reproduction errors. So if I have an input example S times k, the previous input example is k minus 1, the previous weights that I learned here, the weights that I learned then after taking the CDB step, for example, and the outputs, the difference between successive reproduction errors can, in fact, can be defined as a form of surprise metric. And the surprise metric is such that it's related to the second derivative of the posterior distribution of the weights of that metric, for example, through time. So the curvature of the evolution, the posterior distribution of the weights of the SMN through the time evolution. So what does that mean? It means that if this curvature is positive, it means that in the future, the posterior will evolve towards, it will evolve a lot, so it will change a lot. And so it means that the input that you just received right now will cause a lot of change in the weights in the future. And therefore, it means that this input that I receive is highly surprising. I don't know it yet, but I need to change my weights. And therefore, when this S is positive, I will then simply learn this incoming input data in order to obtain the gradient descent step with this input data to refine phi. Conversely, if this curvature is negative, it means that the data point that I'm receiving right now is already known by the system. Perhaps it was a feature that was already seen before because it leads to a reduced probability. It doesn't lead to an increase in the posterior in future time steps. And therefore, when this S is negative, I don't necessarily need to incorporate these inputs into the learning of the system. And therefore, we're just going to do that. We just have this surprise metric, which is the difference between successive errors. And each time S is positive, we simply perform the variances. If S is negative, we don't perform. With a CDP, we just turn on and off. That's CDP. And as you can see, when the surprise is negative, we are assigning, in fact, a Lagrange multiplier of 0 that inputs. Okay. Then, once we had this mathematical derivation, we wanted to try it out with some data to see really what kind of property it has. What we did is that we used the RGB output of our camera to collect RGB data really, as our drone was flying around in the storage aisles. So here you see the storage aisles here. we made our drones fly around, and what we did is that we used the classical, let's say, different learning problem that we solved through just stochastic descent instead of SNN version of it. So just feeding RGB data this time. And so we fed this RGB screen in its natural order, that picture learning is for pattern. And after the end of the flight sequence that we acquired, we simply freeze the weights and we replay the whole sequence back. And we want to see what is the replay error that we are doing at the replay time. And we do this comparison using the surprise method and not using the surprise. What you can see in this graph is that when you use the surprise method, it leads at replay time to significantly lower errors. So in blue, it's the case where we didn't use the surprise. And here you see that in fact the error can peak sometimes very badly, because well, when your drone is, for example, flying in the aisles, it's a long sequence that it sees with all the time the same kind of visual information. So it overfits strongly on that. And then when it gets to the open space, it overfits strongly on the open space. But here using the super, it was really helpful. That's one of the first motivations. A second interesting thing that we observed is stability issues. So it is well known that sports coding algorithms can suffer from instability issues. There's a single paper in the subject here. And what we observed is that indeed, when we were tuning the system for some settings, for some values of lambda 1 and from some dimensions of C, so of the source code that we want to produce, we saw that indeed we run into instability problem as expected by source coding algorithms. But what we observed is that when we would use the Chicago metric, again using the same parameters or keeping all the other parameters the same, just using the Chicago metric, we would get a form of stabilization effect. So you see that in blue, the learning completely diverged at some point. But in orange, when it tries to diverge here, there is a kind of elastic knot effect, meaning that the system is able to get back in track with it. And so we're not exactly sure yet why exactly this happens, but our hypothesis is that this has a form of elastic net effect, meaning that it is well known that if you add a bit of L2 norm polarization on top of L1 norm, you destabilize it. Okay, so now that we have motivated this continual learning technique with this surprise motivation, what do you use it to propose now? So to learn in a continual manner on the real world or real-time stream of data. And using SNN. So now we'll basically use our SNN SCDP framework, which is basically the same as a dictionary learning framework. It's a substrate for dictionary learning problem. We'll use that together with two data sources. Event-based camera data, so DVS data. So we have the positive polarity, the negative polarity. Each polarity is assigned its own SNN STDP ensemble. So this, remember that the first fully connected SNN kind of system that I showed you at the beginning. So these positive polarity spikes have their own dedicated SNN STDP ensemble. The negative polarity has its own ensemble. And then finally, we also have the radar detection that you can see here. They are fed also to their own SNN STDP network. And in fact, the radar detections, well, detections are binary. Either you detect something, either you don't detect something. So you see that we can simply see the detection map as a map of spikes, by considering each detection as a spike and each frame as the succession of the spikes in time. Then what we do is that, okay, we let the system learn to SCDP in that continual manner as the drone is flying out. We concatenate the output spikes of each SNN ensembles. We are doing, in fact, late filtering. And then once we concatenate these descriptors, we average them through time. We get the average weight on a certain time window. We use 50 times time. And then we feed them again to a standard scaling, again, removing the mean each component, dividing by the standard deviation. It's very interesting because it helps you combat some residual covariate shifts that we have in the system. And then these descriptors here that are now of continuous value, because we do the average, are then fed to a red slam backend. So red slam is this very popular slam backend, and quite old in fact, but it's still very popular, that was modeled according to the hippocampus of the rodent, right? And yeah, so it can receive any form of descriptor and yeah, perform slam in a bio-inspired manner, rodent-inspired. In fact, I know that there are some works that have implemented the rest of the backend on slightly on its chips. So, this gives also further information. And also, of course, we feed the odometry data. So odometry is the basically the inertial measurement of the drone. So there is the forward velocity, the angular velocity. And here in this video, which is my last slide, you see the results of the slam. So I will first describe what each box is doing. So here you see the RGB view from the drone. It is not used at all, so it is not given as input to any part of the system. It's just for visualization. You have the even data here coming from PBS that is fed into SMS. You have the radar kind of spiking image, as we call it. And so something that we will do in the flight of the drone is that we will turn the lights on and off. This is to showcase the robustness of the system through lighting variations that we obtain really thanks to the PBS camera, which has a high dynamic range, but also thanks to the radar. The radar is an active sensing kind of sensor, and so it is very robust. Of course, it's completely insensitive to lighting. In this box here, you will have the result of the slam that will build up through time. So the red cross is the point where the drone is. You will have black dots, which will be the walls, in fact, all the obstacles that will be modeled as well. Here, this is just the odometry data, so the raw IMU, the raw inertial measurement is diverging because of the arrows that keep on accumulating. And finally, this box will show you a subset of the weights of the SLM, and you will see that they will change through time. So if you pay attention to that box, you will see those weights really changing plasticity as the drone is flying around. Right? And this will show that indeed the weights are adapting themselves as the drone is flying. So let me play that video for you. And you can indeed see the results. So you need first to see that the path is not perfectly parallel, but as soon as a loop closure is detected, then well, it starts correcting that. It starts correcting also the wall and the black dots here that are, let's say, example. And little by little, the shape of the path here is kind of two, let's say, ellipsoidal path here is then constructed. And the weights, you can see them changing through time. So they were initially randomly reading, and now they start having meaningful features. Something. Yeah. So as a conclusion, so as we covered first this FNNSCP framework that we developed, starting really from an optimization-driven approach instead of a bottom-up approach. And then we applied this SNSCP framework for people detection drones. And then finally, we developed this surprise-driven learning technique and used it with our SNSCP technique for performance slam. So yeah, many thanks to my colleagues and supervisors and for all this stuff here. And also many thanks to Prof. Cohenwex for hosting me here and and thanks a lot to you for your attention. And of course, open for any question.
So you're flying the drone. I mean, it's not. What would you need to close the loop to make it self-flying?
Oh, yeah, we would need then some form of policy that will perhaps it will take the internal states of that drone. For example, the position would be something state that you could also more abstract visualization of states. and map that to a certain action. This would be a typical policy network. You could also use simpler approaches, really, like I would say handcrafted approaches. For example, if you want to go somewhere in the room and you have built the map of the room, well, perhaps you know what were the actions that the drone undertake to go to a certain place, and then you can play them, of course, with some feedback. So you don't want the drone to diverge, and hopefully you can reach the goal. There is a good question. It's in fact what I'm focusing on right now. So now I'm working on the portfolio using active inference theory from corpus, which is really focusing action as well as observation. Really,
You thought at all about how the representations change over time, or what sort of meaningful things you can extract from that?
Yeah, I didn't really go into detail to what my solution means into the explanation kind of side of it. I guess some of them look a bit like the neural parts of the room, somehow in an abstract manner. But one thing is interesting is that I'm not sure about that. It's kind of a hypothesis, but it seems that having neural networks that have their weights continually changing is in fact giving them, making them, let's say, bigger than their bodies. Because imagine that this neural network didn't have its weights changing. Well, it's still a dynamical system, but the space of the dynamical system is kind of restrained. It's only the output of the neural network. But now, since the weights are changing as well, and there are a lot of weights, the state space is way larger, and perhaps it might be an interesting avenue for future research to understand how a smaller neural network can be bigger than its body, can have more expressivity, just because its state space is augmented with also the weights that are changing.
What do you mean by bigger than the body?
I mean that, for example, if you would freeze the weights, it would not perform as well. Perhaps the weight changing, that there's still some oscillations, some residual oscillations. When the learning happens here, the weights don't converge to a certain set of weights and then stop there. They keep on oscillating around a certain stable point. And this oscillation then, of course, impact the output as well. Right? So the output is not only impacted by the input, but also by the weight changing. So that's what I'm trying to say, compared to a conventional neural network, which will not have this feature. So that's what I mean by bigger than body, if it makes sense.
Could you fly your drone in other places and get more natural scene statistics from that? And how would the representations be different, or why are you flying
in this video? So yeah, so the thing is that flying in spaces where you have a certain path makes, of course, a problem a bit more, let's say, approachable. Let's say. So we are doing experimental work with CDP. We wanted to have this kind of setup. That's the first thing. The second thing is that these works are all done really in a kind of industry setting, and we are developing, in fact, drone technology for drone maintenance, inspection, things like that. So that's another reason why it makes sense. But to jump on what you said in your question, what would happen if you do it outside, for example, in a natural scene? It makes the problem very hard, of course. But then it begs the question as well, perhaps if you have GPS outside that you don't have inside, that's why also inside is interesting to snap. Well, if you have GPS, perhaps then it can help you as well. So, but yeah, in our case, it's because, let's say, traditionally we were doing our experiments here indoor. We have well-defined kind of paths that we can then, let's say, learn more easily than the outdoor that is way more diverse, right? You've seen that way. I've seen papers that discuss the fact that somehow when, for example, trees would move because of wind, this can cause problems inside because, well, the visual information changes as well. So There was some paper like that I tried some years ago, which were interesting. So yeah, so this is for these are the reasons why we.
Keep going. Dirk, do you have a question or anybody else who's still here?
Yeah, one question I had was any plans for also doing image classification in the future with this method?
Yes. So we did some kind of image classification here. So although it's spiking images, it's true that those are not like, let's say, yeah, static images. Let me get the slides here. Yeah. So for example, the neuromorphic M-list kind of setup was in fact a form of image classification task. But indeed, you're right. We should in fact look to more complex data sets like image nets, things like that, and make them perhaps spiking by possible coding. Yeah, these are possible. Absolutely.
Great, thanks.
So you're doing online learning basically, but you don't need to, right? Because there's no like feedback from the representation to the how the things moving. So
oh yeah.
So you have, you don't. So how long are you recording for?
Oh, those recordings here are let's say 3-4 minutes of data. This would be the answer. But I agree with you, you don't necessarily need to do continual learning. This is really for, let's say, making the system perhaps more orthogonal, what we say, because we learn things, this is not necessarily the shuffled way. We can learn things on the fly as well. So it has a scientific motivation, it's less of a utilitarian.
But if you had like immediate, like if it was flying itself, you need that in this regime.
Oh yeah, perhaps yes, indeed, absolutely.
So then you could actually make decisions over time.
Yeah, absolutely. That is
Yes, let's stop recording. If you want to save the team, we're going to release the team.
Great.
Thank you.
So thank you, everybody.